The Zoom window? I think, no, I think I know what happened because it was doing it to you too. Yeah. All right. All right. Sorry, we're just moving things around. I've got the chat open too, so I should be able to see what everyone's saying. Okay. All right. Well, hello, everybody. So yeah. So my job, I guess, is going to be basically just to give you just some ideas to think about for the sake of the later parts of the tutorial, okay? So this is just to give you a feel for some Fourier optic stuff as well as wave propagation. So to me anyway, really the point of this, I mean, I know I just said, is to give you a sense of what the later things will bring, but maybe to sort of highlight that more directly. I think maybe 90% of the time, okay, we probably just imagine the camera as just taking one point to a pixel, another point to a pixel. And if we're feeling really fancy, we could add on some Gaussian blur. And for when things are in focus, that works pretty well. Okay, you can't really complain about that. And then if you want to get a little, maybe get crazier, you could add a little Gaussian noise on it. And then that's just plus some Gaussian noise. If you wanted to get maybe even a little fancy, you could do Poisson noise and you could multiply by that. Okay, that's multiplicative. However, for the sake of image formation in the presence of turbulence, this kind of is that 10% where that model no longer applies. You can't form the A matrix so cleanly in the way that we do in the forward model from point to pixel. In addition, you can't just add it on and you can't just multiply it either. So it's a bit more complicated of an operation. So in order then to understand that, we really do have to understand the more along the lines of the true image formation process. Okay, so this is really then what we'll end up talking about. Okay, so to start off, we're going to start really at the beginning. Okay, so so the first thing that I would like you to know about a wave is just that it has a wavelength. Okay, so that's going to be the distance between two peaks. You could also define it another way, just the distance between two identical neighboring phase locations. However, two peaks is easy enough to say. Okay, so we'll just say two peaks. So this is going to be in meters. But this is kind of a bit boring, okay? It's just a wavelength. It's not really all that interesting. A bit more interesting is that waves move, okay, through time. So here I have two examples of waves. One is a slow-moving wave. Another is a fast-moving wave. So on the right, you can, if you were to, imagine that you're standing on the right here, okay, looking at the wave on the top, looking at the wave on the bottom, you would probably notice that the wave on the bottom is appearing to fluctuate faster. However, if I was to pause this animation, you would see that they have the exact same wavelength. So my point being here is that not only is the wavelength an important quantity, also the speed at which the wave moves is an important quantity. Now, for the sake of light, you might say, okay, light moves at a constant, okay, in a vacuum, all right, all good. But for now, we're speaking a bit, I guess, more generally about waves. So for now, we're going to allow them to have slightly different velocities, and then we'll narrow in on light in a bit. In addition, this will be really the most significant idea, at least up front, that we'll talk about, which is going to be this complex representation of a wave. So in this case, my wave that I'm showing on the upper right here, that's going to be u of x of t. I can use my little pointer here. U of x of t, this entity right here. Now, there's two things that we're going to divide up into. One is going to be the time evolving part of the wave. The other is going to be the spatial part of the wave. Okay, so u of x in this case will be constant, whereas it's really just going to fluctuate in time. More interestingly, we can move to spherical 2D waves. Okay, so we can talk about primarily spherical waves. Maybe just for the sake of time, I'll go a bit fast through this. Basically, no longer is our complex envelope, capital U of x, constant. It now can vary. So, and in addition, you could add on a little time component, and it would also vary in time as well as space. So this starts to give us maybe an idea of if we're going to write, let's say, a wave equation, that is to say, a wave that describes the motion of a wave, then we have to take into account both the spatial relationships and the temporal relationships. Okay. Yeah, sure. Question. What is U of X here? So in this case, it is very similar to this case, U of X. So it would be a complex representation. It would be, for example, there's 3 examples here. A of O over magnitude of X, this kind of thing. Really what it is this is going to be the complex amplitude of the wave. So it has something to do with, we'll get more to exactly what that means, but it has something to do with the energy that is going to be carried by the wave. So, and in the case of a spherical wave, if my source is on this wall, by the time it gets to me, it's decayed by a factor of 1 over the distance. And by the time it gets to you, it's decayed by a factor of 1 over the distance. And that's related to the, what was that? Oh, A0. A0 is a constant multiplicative thing. The decay is really going to be related to the fact that it's divided by magnitude of X. So the fact that it comes to me and it has a certain energy, and it comes to you and it has a certain energy is a result of that. So, but this is really just a way of describing the way that the energy is carried by the wave. That's really what this is getting. So, yeah, okay. So a wavefront is going to be a critical concept to sort of wrap our heads around. So, but just taking the case of a spherical wave here, if I fix the phase angle at a particular angle, and I were to sort of go throughout all the space, okay, and I go, okay, the phase at this particular point is 11 pi over 6. I'll put a dot there. I go to the next point, put a dot there. I'll end up drawing all of these lines, okay? And what that will give me is these wavefronts. So in between the wavefronts, if I draw a perpendicular line from one to the next, that will then be the wavelength, okay? So, and this K multiplied by magnitude of X, that's going to be, the K is going to be my wave number. This is sort of a way of converting meters into radians for the sake of the wave. So that's just a little bit of background about waves, just so we have a few kind of ideas in our minds to talk about, okay? So let's talk about the wave equation. When I just have a spherical wave, that's all fine, okay? But maybe if I put something in the way, then I'm going to start running into issues. The reason is, as we'll see very shortly, it ends up being a differential equation that we have to solve. So I would need to know that then the boundary conditions. So then I have to solve a differential equation with boundary conditions. Okay, so it's not just as simple as writing u of x, 1 over x e to the power of whatever. Okay, then I have to think about the boundary conditions. So just to give you a bit of a feel for the one-dimensional wave equation, if I have a particular, let's say, shape of a wave propagating through space, either in a fast manner or in a slow manner, I'll represent the sort of the kernel that I'm moving by g of x, and then the wave in space and time is f of x. Really what I'll do is I just want to describe a way that links both the spatial behavior and the temporal behavior. Remember that the wave both exists in space and time, so we have to kind of carry those things in careful consideration of each other. So if I end up taking the partial derivatives of these moving waves with respect to space and time, I end up doing it twice, we'll get this wave equation, okay? So this is going to be my challenging, this is going to be the source of all my problems, okay? This is why we're going to have to make a bunch of approximations, because we have this very irritating differential equation. Now, in the case of, like, let's say the spherical waves, we can do kind of what we did before. We split the two things up into a spatially varying component and a temporally, or time, varying component. And if we do that, and if we were to drop it into this equation right here, of course, in a higher dimension, we end up getting the Helmholtz equation. So what this is going to do really is it's just going to say, all right, ignore the fact that it's evolving through time, okay? And let's just focus on the spatially evolving part of it, the spatial behavior. That's really going to be like the critical thing, okay? Because if I'm interested in how does a point source on, my shirt get to you, do I care about how it's fluctuating in time? Yeah, but at the end of the day, I'll just multiply it by e to the power something t, and then that'll take care of the time part. The more difficult part is going to be the spatial component. So that we're going to focus primarily then on the Helmholtz equation here, which quantifies the spatial component. So we're assuming that it's separable here. Okay, so this is kind of a lot, I guess, of information. And then honestly, I'm just going to kind of throw it away and make it much simpler. But it's just to give you a sense of this really does come from somewhere significant, okay? And it is hard to solve these problems, but now we're going to do it in a much easier way, okay? So this is going to be the Huygens-Fresnel principle, all right? So really what we're going to do is for every single thing pretty much we're going to do from now on, we'll just think about the two following things. First of all, I'll assume that sources of waves radiate out spherically, okay? That's a pretty simple assumption. The other assumption is every single point along a wavefront can be considered a secondary source, which we'll refer to as wavelets, which interact. And then we'll add up those wavelets and we'll get where the wave will be at the next instance of time. So as you can see in this little diagram here, if my wave runs into this screen, I'll end up drawing a bunch of dots here, and then I can just draw little circles at these dots. And then if I eventually want to say, okay, what does the wave look like after the screen at a certain point? I'll basically just trace these circles, and then I'll know. Okay, so it's actually very simple. It's just kind of a graphical way of doing this. And this really simplifies this Laplacian of u of x, blah, blah, blah. That's very hard to think about. For me, just thinking about drawing circles and then connecting, that's much easier to think about, okay? I would like to acknowledge that this, technically, the equation that we're using here, I'm going to refer to it as the Huygens-Fresnel equation. However, in all honesty, it actually is, by using this very fancy equation, I can end up getting this equation right here. But as you can see, it really is just a sum of spherical sources, right? If I have a particular distribution here, I'll integrate and I'll sort of add them up with respect to the spherical component, and that will give me my wave at another location. And it's also reflected in this diagram as well. So yes, it's the Huygens-Fresnel principle. And if a physicist tells you, the Huygens-Fresnel principle, that's old stuff, say, well, I'm using the Rayleigh-Sommerfeld equation, but I'm just thinking about it as the Huygens-Fresnel. Okay, I know you won't run into that situation, but just for sake of argument. Okay, so diffraction. This is really where we're going to need this wave idea in order to solve this problem. So here's going to be the situation. I'm going to have a point source on the left, and it's going to pass through some sort of screen. Okay, and you might say, why would I want to do that? Okay, that seems like kind of an arbitrary problem. But then as soon as I sort of change the shape to be more hexagonal, and compared to the camera, you go, oh, okay, then maybe that actually does start to make a bit of sense why I'd want to do that. Okay, so but first we'll just start with the square. That's gonna be much easier. Okay, so let's assume that I have a point source. The wave is going to be landing on this diffracting screen with the hole in it, with the square in it, and then I'm going to be standing pretty far away. Okay, maybe I don't know, 1,000 meters. Okay, pretty far away here. So everybody, just take a second in your mind. Okay, what do I expect to see if I'm 1,000 meters away? What's it going to look like? Okay, just take a second and think about that. I have my guess. I know the answer, and I'm still going to I'm still going to guess it wrong because it doesn't feel right. Okay, so you have your guess. All right. I would expect it honestly to look like a square, but it ends up looking like this funny star-looking thing. Okay, so we'll say that the wave diffracts at the aperture, and that this is a result of diffraction. So this is kind of my expectation versus reality. Okay, and my mind is, the cogs in my mind are turning. Oh, why is this going on? As we'll see, it ends up actually just being, especially if you're really far away, it ends up just being the Fourier transform. Okay, but the question as to why is the Fourier transform, that's really one of the core ideas that we want to get at here at this first part. Okay, so why is this happening? It's a very odd thing. Okay, so let's do Huygens-Fresnel for diffraction hitting a wall. Okay, so not only is our wave going to be hitting this wall, okay, the wave is coming hitting a wall, we're also going to hit a wall as far as the mathematics are going to be concerned. If you were to really write this down and try to do this summation of spherical waves, you'll quickly become very angry, okay, because you're not going to be able to solve this. Okay, if you do, let me know. Okay, but you're not going to be able to solve this. I'm pretty confident in that. Okay, but so now the question becomes, okay, well, you just told me all this great stuff. You told me the Huygens-Fresnel principle. You gave me a practical situation in which I would want to know when a point source is running into this diffracting screen, why I would want to know what's happening at a distance far away. But now I can't do it. Okay, that's kind of irritating. So, okay, so then there's someone who is very clever. Okay, very, very clever. So he's taking all these ideas into his mind. He goes, okay, a spherical wave, if I let it go out far enough, it kind of starts to look like a parabolic wave. And if it goes out even further, it starts to look like a plane wave. And he also has this equation, and he's angry like us, okay? We can't solve the problem. And then he has this idea, oh, I know what I'll do. What if I just ignore when the red screen is really close to the diffracting screen? So essentially, go for it. Oh, what's wrong there? Yeah, so it'll end up being the R. Well, he just, yeah, it'll end up being the R and the psi. That's. Say that again. Correct. Yeah. Oh, yeah, this is a good question. So yeah, I don't think we have written that directly. I think in maybe a later slide, we do have that, but no, you're absolutely right. So yeah, the difficulty is that R ends up being a function of the distance between 2 points. So it ends up being a function of basically psi. Okay. So because of course, really what he's asking is, why can't I just factor out exponential JK R over R and then just integrate over the square? You know what I mean? That doesn't seem that hard. But the problem is that R is also a function of the integration variable, the variable of integration. That's his question. So but Fresnel says, well, what if I just ignore when the red screen is close to the diffracting screen? And then I don't have to worry about all the difficulties. It'll still be a little difficult, but I can maybe get around it, okay? So here's our situation. We have a particular screen, and we'll just say of arbitrary shape, sigma. And then I have some sort of complex wave arriving at that screen. And I want to know, okay, if I do all my summations, right, my Huygens-Fresnel principle, but I just make them parabolic waves, can I solve the problem? Okay. So what he ends up doing is, if I make this assumption, and there are, if you go on the website, download the slides, there actually are bonus slides stepping you through this derivation. But effectively, you can make a few extra sort of approximations and cancellations. And he ends up finding that the pattern that's going to form at a particular distance will end up being the Fourier transform plus a few extra friends along the way, okay? So this is going to be Fresnel diffraction. This is our first kind of big result. So now we really don't have to think about this sort of, for one, the complicated Laplacian equation, the differential equation. And we also don't even have to think about this equation that was just causing the problem in the last slide, this equation right here. We can just think about basically the Fourier transform, okay? Now that seems like a pretty good success, but I like this next guy even better because he's even in some sense lazier, okay? I really like this. So he says, what if I put the red screen really, really far away? Well, then I don't even have to worry about parabolic. I can basically just use plane waves. Now that's much easier, okay? So this effectively lets us cancel out one of the terms of the Fresnel diffraction, which then gives us a really interesting result, that the pattern is basically going to be just the Fourier transform of the aperture or of the wave distribution at the aperture, okay? This is a very kind of odd result that I know that I would not expect. You know, even when I was reading this the first time, I was like, oh, that's kind of odd that it ends up being a Fourier transform. Something very, you know, sort of common to us in the, you know, electron engineering community here. So, so just comparing Fraunhofer versus Fresnel, where are these two things valid? Okay, so remember that these are the results of approximations. So if I've made an approximation, I better have some way of knowing when to use it, okay? So the idea is that Fresnel, the Fresnel approximation is going to be valid for a larger region, okay? And that's because he didn't cheat as bad as Fraunhofer, and he used parabolic waves. So it's going to be valid for most regions of interest. However, it's going to be a bit complicated, right? Because it's not just the Fourier transform, it's the Fourier transform plus a little bit extra, right? Fraunhofer, that's really the equation that we like, okay? But it's valid further away. And he used planar waves to do this. It's easier, but really then the question in your mind should be, is this even useful at all, okay? Because when am I ever really standing infinitely far away from something? That seems like sort of an odd scenario, okay? But anyways, bottom line, take the Fourier transform of the aperture, that would be what you get at the output. Okay, so just to recap, we've talked about waves so far, all right? So wavelengths, optical frequency, Huygens-Fresnel principle, how a spherical wave can be approximated by a parabolic wave and also a planar wave. I'm also burning enough time so that the animation can play because I really like that animation. The Huygens-Fresnel principle. Okay, so we've talked about waves. And in addition, we've also talked about really what's going to happen is if I have a point source running into a diffracting screen and I'm a certain distance away, it'll basically just be the FFT. Okay, now you might be thinking, I've left out a critical part of my camera imaging system. I forgot the lens, okay? And as we'll see, the lens is really going to make things very simple for us very shortly, okay? So now we're going to get into imaging. So how is a point imaged, okay? So let's go ahead and add in the lens. And also just to give you a bit of a preview, really we'll kind of talk about turbulence in a very similar way as lenses. A bit more on that, of course, later, but we'll basically just view the turbulent medium as just a distribution of very complicated lenses, okay? So let's say I take the case of a plane wave hitting a lens. So let's do it with the Huygens-Fresnel principle. That's my favorite way to do this, okay? So, okay, let's draw a bunch of circles. But hang on. Light does not move through glass at the same speed as it moves through free space, okay? So I've already made an error, all right. So then I go, oh, okay, well, now I have to take into account that it's moving through glass. But really, that isn't all that hard, okay? So let's just talk about some of these points here. This point near the top is going to propagate through space, free space, longer than this point here. This is going to immediately start going through the glass. So really how I'll start to think about this is the points towards the outside of the lens will have a very, very small time delay, whereas the points that are passing through the thickest part of the lens, those will have the biggest time delay. So what does that translate into for my Huygens-Fresnel principle? Basically, this particular point will get a big circle. This point will get a slightly smaller circle. That one will pass through the thickest section of the lens, so that will get the smallest circle. And then they'll start to increase towards the end. Oops. And you can see that if I actually draw a line tracing the edges of those circles, I end up starting to get no longer a planar wave, but it starts to get a little bit of a curve in it, right? It starts to become maybe a parabolic or maybe even a spherical wave. So then you can do this again for the sake of me making the animation. I don't want to do it again, okay? But you can do this again, and then you get the output wavefront. Now, the wave has no idea that it was a planar wave. It just does whatever the Huygens-Fresnel principle tells it to do, right? So if I were to draw this sort of thing here, to itself, it looks like a spherical wave. It says, I've been a spherical wave my whole life. I've never been a planar wave. It doesn't know the difference. So if I start to draw the circles again, it goes, well, I shouldn't propagate according to the fact that I was a planar wave. I'm a spherical wave. So I'll simply just keep going in a spherical pattern until eventually I just sort of explode at the center there, and that'll be my focal point. Okay, so that's effectively what a lens is doing, is it's tricking a wave that was planar into becoming spherical, and then all meeting at a particular point. That's what a lens is doing. Okay, so then maybe there's a question in your mind, who cares, okay? But this is really then where it's going to get awesome, okay? If I was a planar wave, let's say I draw 2 points on there and I draw rays, okay, emanating out perpendicularly. Where would those 2 points intersect? Okay, you might say never. maybe if you're really into some classical computer vision stuff, you might say a point at infinity, okay? However, after the lens, those two rays, they're no longer going to intersect at infinity. They're going to intersect at the focal point. So what does that mean? That basically means that whatever was going to happen at infinity is now going to happen at the focal point. And what do we know is going to happen at the focal point, or rather at infinity? It'll be the Fraunhofer pattern. So what that really ends up meaning is that after the lens, we'll end up getting the Fourier transform at the focal point. So that's really our critical result here, is that for the sake of imaging, the impulse response to a single point is going to be the Fourier transform. So what does this mean for a circular aperture? Okay, this is going to mean that if I take the Fourier transform of a circle, I end up getting the airy disk pattern. Okay, so this is actually why the Gaussian approximation works so well, is because this ends up looking basically like a Gaussian kernel. Okay, however, you'll see in the case of turbulence, this point spread function is no longer going to look Gaussian. It's actually going to look very chaotic. Okay, so we'll have to know that we need to take the Fourier transform in order to understand what that point source is. So just looking ahead a little bit. And this gives us also an idea of the limit imposed by the fact that light propagates as a wave. This will be the diffraction limit. So the diffraction limit is effectively just going to be the width of that main lobe. So it's going to be related, as you can see, by the wavelength as well as the focal length and the aperture size. So now there might be a question in your mind, okay, well, if I'm limited in my imaging by the aperture size, why don't I just make the aperture size really big, okay? Make it huge. And that's not a bad idea because widening in the spatial domain will mean shrinking in the Fourier domain, okay? And since I know that the Fourier transform of my aperture gives me my impulse response, I may as well make the aperture really big. Now, technically, an infinite aperture is impossible, so you're never going to get around this sort of diffraction limit. But that's why we make our apertures really big when we're trying to image something far away, because we need to shrink down that pattern as far as we can. So if I can make it big in the spatial domain, I take the Fourier transform, it'll become small in the Fourier domain. That's the idea. Okay, so now let's talk about image formation. So basically, an image or an object is just going to be just a set of point sources, okay? So I'm going to have a point that's going to emanate from the object. It's going to land upon my aperture. And then what I'll do for each one of these points, I'll say, okay, this point source, I'll take the Fourier transform of the aperture and I'll drop a little bit on my pixel plane. This point source, I'll take the Fourier transform of the aperture, I'll drop that on my pixel plane. I'll sum them all up. But that ends up starting to look like convolution. Okay. Now we've made an assumption. We've sort of made a jump, and I don't know if you necessarily caught it, which is we kind of went from talking about incoherent stuff, or rather from talking about coherent stuff to talking about incoherent stuff. So really what we've done so far is we've used coherent wave optics. We've just used the Huygens-Fresnel principle of these things in order to get from the wave being at one point to the wave being at another point. However, now all of a sudden I'm talking about just a normal imaging system, which of course is not coherent. So as we'll see very soon, the two things are actually very much related. Okay, so we can use all of the coherent stuff, all of the Huygens-Fresnel principle stuff in the way that we've already talked about it, and then sort of do a very simple operation in order to know the incoherent imaging system, how that works. So here's basically what it means for us. Coherent imaging is going to be convolution in the wave domain. This is basically the Huygens-Fresnel principle. Incoherent imaging is going to be convolution in the image intensity domain. So like someone just held up their camera right there, took a picture, okay? Really, that's going to be incoherent imaging, okay? That right there will be incoherent imaging. He doesn't have a laser pointer or anything like that, okay? So he's not doing anything all that fancy, right? He's just holding his phone up, very sort of simple thing. That will be incoherent imaging. So really the thing that we're used to is going to be this incoherent imaging. How are the two related? basically we'll analyze the system using wave optics. This will give us some sort of transfer function, h of x. And then simply enough, we'll just take the magnitude squared of that. So our big equation is going to be this. I have an object, and is it worth describing what I of g is? Probably not necessarily. You can basically just think of it as a clean version of whatever you're looking at, a perfect representation of what you're looking at. I'll take that image and I'll convolve it with my diffraction kernel, and then I'll get the output image. Okay, so really I can think about things almost in the same way as I said them all the way at the beginning, which was, sure, question? What? Say it one more time, I'm sorry. Diffraction will influence it. So, and the way that it influences it is, let's say like pure wave diffraction will give me h of x. Okay, so I have a point source. As far as the waves are concerned? Yeah, okay, so let me go back a slide then to talk about that. So basically, the wave, okay. Yeah, okay, sure. So let's take the case of a laser. So, okay, let me actually maybe expand on the question just to sort of fill everybody in, also those virtually. So basically the question is, effectively, what's the difference between incoherent and coherent, right? Another thing that was just said was, why are the waves messy? Okay, so let's answer that. So basically, everything we've done so far is about understanding how a wave gets from one point to another point. Okay, so we've done Huygens-Fresnel principle to do that. So of course, you would say that in that case, of course, this is also one of the axioms in some sense of the Huygens-Fresnel principle, that you can solve this by wave propagation and superposition. So that is to say that it's linear in the wave. Okay. Now, when is this situation going to be the case? This is going to be when a wave is very carefully emitted as either a point source or in a laser. So it actually takes a pretty good amount of effort to design a laser, right? And the reason is because it has to obey this principle that all of the waves are allowed to interact with themselves. And the reason that they interact is because they are very carefully designed to all sort of be in a particular relationship to one another, which is a perfect represent. It is. I guess. Yes, exactly. So it was assumed that it was like a perfect coherent wave hitting the diffracting screen that then gave me the Fraunhofer pattern. It absolutely was, because a planar wave, truthfully, is a coherent wave. Okay, so coherent waves, maybe you can just think of them as planar waves. Okay, that's maybe that's not exactly true, but you can think of it that way. Now let's go to incoherent imaging. Okay, let's just take I like using the wall as my example here, I guess. Okay, so let's take the case of this. There's a bunch of lights in the room. Okay, there's this light on the screen. There's all these sources of waves. Now they're all going to kind of end up landing right here. Okay, now if you're going to tell me that that light knows what that light's doing, knows what that light's doing, knows what this computer is doing, and they're all emitting in a careful enough way that they're going to all add up in a very clean way, I'm going to tell you you're crazy, okay? Because, yeah, I mean, you'd effectively be saying that someone has designed this room so carefully that all the waves will interact in a perfect manner at every single location. The fact is, it doesn't have to be from 2D to 3D. It more has a fact to do with the, it more has to do with the phase, exactly. So it's something like, I like to think of it in this way, like a fire, okay? The photons are emitting sort of spontaneously, okay? They have no respect to what the other one is doing. Whereas in a laser, they're being carefully emitted in a way that they're all being emitted where their phases are sort of being emitted relative to each other, so that at another point, they all can remember what they were, because it's just a phase difference as far as propagation. But with the fire, it's all going to be coming out very chaotic. So of course, they'll combine in a very chaotic way. Now, that's why the waves are messy. Now, as far as why does that, if I go forward here, why does that mean that then I take the magnitude squared? Because that's a jump. I recognize that that's a jump. That I'm not going to answer here. There are bonus slides about. Well, I take that back actually. But where you can read about this, I guess if I can highlight it, would be Joseph Goodman's book is a great example of this. It ends up being basically that you take the expectation, one in the wave domain, the other ends up being that you can move the expectation outwards, and that some things end up canceling out, and then I can get this equation. So basically, everything I've done as far as Fraunhofer pattern, these things were coherent waves, but there is a nice sort of clean relationship between coherent and incoherent as far as imaging is concerned. That's sort of the answer to your question. Okay, so really what this means for us is that whatever the object looks like, I'll just convolve it by the Fourier transform of my aperture, and then I'll get really what it'll end up looking at on the camera. Okay, so in the case of a circular aperture, I'll have a perfect object. I know that my camera is circular, so I take the Fourier transform, and then I convolve it with this circular pattern, this almost Gaussian looking thing, and then I get maybe a slightly blurry image. So here's just an example of that. Just, I guess, to finish up this Fourier optics stuff, let's just take a look at the optical transfer function. I know we're getting close to the break time here. So basically, if I want to look at my camera system in the Fourier domain, I can do sort of kind of this weird, ends up being this weird relationship. This is kind of the foundation of Fourier optics in some sense, is basically, I want to know what frequencies are going to pass through my camera. Okay, so let's say if I have a little small lens, of course, I'm not going to be able to image all that accurately because a small lens will mean a large point spread function, whereas a big lens will translate to a small point spread function. So, but basically I want to quantify this in more of a signal processing sort of way. Okay, so maybe these horizontal, or rather vertical lines on the wall over here, they're moving at some sort of frequency, and I want to analyze, can that particular frequency pass through my imaging system? That's what I want to analyze. This is basically going to be what the optical transfer function is going to be. And interestingly enough, I won't go through it just for the sake of time. It ends up just being the convolution, really in this case, the correlation of your aperture, okay, in the frequency domain. So I can't say that it's exactly your aperture, but it's in the frequency domain. So a circle ends up turning into kind of a carnival tent looking function, and then a square ends up looking like basically a pyramid. But so as far out as that passband extends, that will correspond to the maximum frequency that is accepted by my imaging system. So I can use all these ideas sort of in a very typical, electron engineering signal processing sort of way. All right, so just to summarize, the point spread function basically just comes from the shape of the aperture and has to do with how the plane, how the wave lands on the aperture. Okay, so far we've assumed it lands flat. In the next part, it will no longer land flat, and that will be the source of our problems for turbulence. So this is a result of Fresnel and Fraunhofer diffraction. So if you image through a random medium, this lens that we talked about is going to become very complicated. So that's going to really be the source of our problems. But so in order to understand this, we needed to understand the lens. So that's why we did all that. So in summary, perfect image, take the Fourier transform of your aperture, do the convolution, that'll be the image you get on your sensor. So, okay. And I think perfect time for the break. Literally. Okay, we got it.
Thank you.
I'm stuck. I'm stuck. Oh, there we go. I don't know how to stop recording. Oh, there it is.